Hello everyone, my name is Christian Dam Vedel, and I'm the third ESR in this design project. This is my first video, and it will mostly serve as an introduction as well as an overview over my focus area in the overall project. Firstly, a bit about my background. I'm from the Scandinavian country Denmark. It's the country marked with a red flag on the map, in case you don't know it. I took my bachelor and master's at the Technical University of Denmark, DTU, with a focus on quantum technology and atomistic simulations. In fact, my thesis was the conclusion of a collaboration with Synopsys Quantum EID department in Denmark and CEA, Centre d'Énergie Atomique in Paris. So in fact, this design project is already my second EU project and also my second project with Synopsys Quantum EID. At the moment, I'm staying in Glasgow in Scotland, working together with my fellow ESR Christina Martinez and our supervisor Vihar Georgiev. So, my overall role in the design project is making the atomistic simulations for the group, but I'm also the designer of design. I'm sorry for the pun, I couldn't help it. What I mean is that I'm the webmaster of our website and the designer of these videos. But my primary focus is still on the research, shown here. Specifically, I'm making simulations in two key research areas. The first of these is the growth of the III-V semiconductors, with an emphasis on the defect formation dynamics. The goal is to mitigate their formation, or maybe even control it for desired material properties. The second key area of my research is what properties these defects give to the material, such as how different types of defects influence things like conductivity and bandgap. So, I've started out by investigating indium phosphide because it's a binary III-V compound, so it's simple to simulate. Indium phosphide has two key phases that are almost energetically equivalent. Zinc-blended, which is like the diamond structure for binary compounds, and wurtzite, which is a hexagonal lattice. Zinc-blended is the bulk ground state, but the phases are close enough in energy that wurtzite can randomly occur in growth. This is seen as in the ground structure as a stacking fault, since the primary difference between the two phases are the differences in the stacking. So this kind of defect would be a missing C layer in the zinc-blended stacking, for example. The goal of my investigation into this is to control the growth to avoid these stacking faults, or maybe even to mix the phases intentionally. You see, wurtzite and zinc-blended has different bandgaps, and by controlling the phase, we can therefore control the bandgap even though it's a binary compound. Controlling the zinc-blended and wurtzite phases becomes even more interesting when working with ternary or quaternary compounds. As you see on the graph shown here, the metastable wurtzite phase often has a direct bandgap in the entire composition range, as contrary to its zinc-blend phase. This opens up the possibility of having efficient emitters in the green gap, which is the overall motivation for controlling this phase. So, at first, I naively tried to simulate the indium phosphide growth using molecular dynamics in quantum decay with the included test of potential. I quickly realized that the test of potential wasn't advanced enough to catch the difference between the wurtzite and zinc-blend phases. I then tried to make my own potential using machine learning with the moment tensor potential method. In this method, atoms are defined by the environment, so the raw data for the machine learning process has to include structures with various physically significant environments. The raw data then has to be filtered in case a majority of structures are too similar, such as having an equal amount of atoms. The raw structures are then calculated using expensive and accurate DFT methods, and the potential is trained to replicate these structures' energies, forces, and stresses. Finally, the potential is tested against an independent validation set, and if need be, more structures are generated to refine the potential. The good thing about this method is that it is iteratively improvable, and it is possible to get DFT accuracy using the much less resource expensive molecular dynamics method. So I did this iterative process 8 times in total, continuously refining my potential whenever it failed a validation test. For each iteration, I sweep the machine learning fitting parameters to find the best fit to the data. In the end, I had more than 1,600 DFT calculations in my training set. One of my validation tests was my potential's ability to replicate the equation of state, which is what I show in the 2 graphs here, where you can see a clear improvement from my 2nd to my 5th version of my potential. While I was finishing some final adjustments on the machine learning potential, it was brought to my attention that we should probably simulate the growth as an atomic layer deposition process rather than a chemical vapor deposition. This is what I'm currently working on instead of the molecular dynamics, and my initial results have just started rolling in. All this time I spent developing a potential wasn't spent in vain, because I'm currently using it for my other research area, which is calculation of the resistance associated with stacking fault grain boundaries. In these simulations, I use the machine learning potential to relax my structure, effectively saving me days of calculation time, because these structures can be quite big. I calculate the resistance across the boundaries using the non-equilibrium green function method, as implemented in quantum ATK. Shown here is an example of the grain boundary and the electrostatic difference potential of the device region. So that was my introduction to my work, and a brief look at what I am currently working on. If any of this was interesting to you at all, make sure to bookmark our webpage, shown in the left, down here, if you can see my finger. And follow us on LinkedIn and Twitter, as we will post updates of our research there. Also, feel free to contact me on my email, shown here, if you want to get in touch for scientific discussions or anything else entirely. I hope you all enjoyed the video, and I'll see you in the next one. Cheers, everyone.